introduction, and thank you for inviting me to speak today. It's great. Okay, so I was thinking hard about what to present. So, and here's a list of some of the projects I'm doing, and as you can see there is something common across these projects. So they're all around developing AI or optimization methods and then actually applying them to real world problems. And a lot of the work I do is actually with industrial partners, as indicated here on that slide. And industry partners, they either fund the research, provide advice, provide data sets, and so on. Yeah? So I thought, okay, which of these topics should I present? So I decided to present not only on a single topic, but I decided to group four topics together and provide an overview of these 4 topics and how we have tackled them. And these 4 topics, they have something in common. So all of them have in common that they involve expensive, time-consuming, or resource-intense evaluations of solutions. Yeah, so today I'm trying to say something about each of these 4 topics, though I may not manage to do one of these topics that are the ones on safety constraints. Though I have the slides in the back of that slide there. Here's a brief agenda of what I'm going to discuss. Brief introduction to expensive optimization, and then I will talk a bit about Bayesian optimization. And then I will provide an overview of these 4 topics. Yeah, I will tell you something about these 4 topics or challenges in experimental optimization, and then also how we have tried tackling these challenges. Yeah? And some of these challenges will be new to you. Yeah, I think perhaps all of them will be new to you, which is good. Yeah. So in expensive optimization, that's the situation we're having. We have typically a computer on which we have an optimization algorithm running, and the optimization algorithm optimizes a problem similar to this one. Yeah, the formal definition of a problem, where f of x is your objective function and x is your decision. Your vector of decision variables, and capital X is your feasible search space. And then we have the computer is suggesting a solution X to be evaluated, and an expensive optimization that may involve a time-consuming CFD simulation, or actually, if you're trying to optimize the taste of food, it may involve actually tasting a sample of coffee or chocolate or whatever it is you're trying to optimize. Yeah? And in drug discovery, it could be actually mixing a number of drugs together and testing out their potency and side effects. Yeah? But also in tuning of machine learning algorithms, for example, neural nets, these evaluating a particular neural net configuration can be actually very time consuming. Yeah? So that can also fall under expensive optimization. And once these evaluations are done, the objective function is then returned to the computer or the algorithm and then considered in the generation of a new solution. And that loop is repeated until we're running out of budget, money, resources, and so on. Yeah? And the interesting bit about expensive optimization is also that often the objective function values are noisy. For example, taste of coffee. If you have a panel of experts that are trying, for example, the different types of coffee, then you will have variations across their preferences over one coffee, preferences from one coffee to the other. And we can also have multiple objective functions, and then we're in the domain of multi-objective expensive optimization. Yeah. So, and this is the space I'm finding myself working in here. And these evaluations are time-consuming, as I mentioned before, costly or resource-intense. Yeah. So that's the setup we're finding ourselves. And in reality, we would simulate, of course, for example, in optimizing the taste of coffee. If you're developing an algorithm, then you cannot validate and compare different algorithms, of course, with using real humans, because you are limited in the number of evaluations you can do. So you're simulating, in essence, an expensive evaluation using typical test functions as we have out there. Sometimes you have to design customized test functions. If you have an expert at hand, they can help you design that test function. Ultimately, you want to pick the algorithm that you think is doing best on the real problem, but you're using cheap test functions to then validate and develop an algorithm. Yeah. So a few considerations in experimental optimization, and these considerations we may not have in a non-expensive optimization problem. Yeah? So speed is very important in experimental optimization, because every evaluation is costly or time consuming. So or resource intense. So you have typically a limited budget of resources, limited budget of money or time. Yeah? So you need to converge to a near optimal solution as quickly as possible. So we use, for example, greedy variants of evolutionary algorithms or Bayesian optimization. And in fact, Bayesian optimization has become the state of the art and the default approach to tackle expensive problems. Also, you want the solutions that you at the end identify, you want them to be reliable in the sense, for example, if you're dealing with a drug discovery problem, then the drug at the end you have discovered, you want this to be reproducible. Yeah, if you manufacture this many times, you want the potency of the drug and also the side effects to be stable. Yeah, you don't want the drug where the potency varies a lot or the side effects vary a lot. Yeah, you want to be sure that the outputs are as consistent as possible. And also you want to have robustness. Yeah? There is no point in developing a product, let's say a drug combination, that actually can't be manufactured because it's just far too expensive. Yeah? And often also in expensive or experimental optimization, we have a reference solution. Yeah? Again, think about the drug discovery problem. Typically, we would be using 96 well plates where we would test different drug combinations, but then also some of these well plates would be filled with control samples. Yes, so to understand whether there are any variations due to temperatures or other hidden factors. Okay, so Bayesian optimizations. Some of you may have heard about Bayesian optimization. As I mentioned before, is a very popular approach to deal with expensive problems, and is derived from the design of experiments community, yeah, which is quite an old community, and the first people that were talking about Bayesian optimization or triggering, that was, I think, in the 1970s already. Yeah, but that approach has become popular only in the last 10 years or so, yeah, really, Bayesian optimization. And it's a sequential design method, unlike to, for example, evolutionary algorithms where you have a population of solutions. In Bayesian optimization, you typically have one solution at a time. And there are two main components in Bayesian optimization. It's the statistical inference method and the acquisition function, which we also call the infill criteria. So the inference method is, in essence, allows us to build a surrogate of your objective function. And in Bayesian optimization, that's typically a Gaussian process regression. And that surrogate allows us to essentially evaluate the quality of a point at an unseen location. Yeah, it allows us to extrapolate. It allows us, the GP gives us the predicted mean value of that objective function at a particular point, but also the uncertainty in that mean value. Yeah, so these uncertainties indicated here by these blue sausages. Yeah, and here the dashed line is the mean value, and the solid line here is the solid line here is the true objective function value, yeah? Which of course we don't know. Okay, and then we use that surrogate. It's called also a surrogate, our Gaussian process. Then we use the surrogate to define the acquisition function. We use the acquisition function to decide what's the next point we want to evaluate in real world. Yeah, and evaluating points using the surrogate is very cheap. Yeah, but we use that surrogate to decide what's the next point we want to evaluate in the real world. And a typical acquisition function then is, for example, the expected improvement. Sorry about that. Okay. So, and every time you evaluate a new point, you then include this to your sample and you build a new surrogate. Yeah, and over time, your surrogate becomes more and more refined. Yeah, and more similar to the real underlying objective function, which you of course don't know. So in the meantime, Bayesian optimization has been extended to many different fields. For example, these days people use Bayesian optimization to do also batch evaluations rather than point by point. We also can handle constraints in Bayesian optimization, mixed type variables, multiple objectives, and so on. Yeah. Okay. So now I'm going over to some of the experimental challenges. Yeah? And the first one I'm going to start with, yeah, it might be worthwhile saying all of these challenges are actually challenges we have seen in actually real life by working with biologists or companies. Yeah? So these are not made up things. So the first challenge is change of variables during search. So this is This was work I've done actually during my PhD with our biologists at the University of Manchester, and that was the drug discovery team. So what they wanted to do is, they knew individual drugs are quite potent in tackling a particular disease or condition, but they thought, okay, why don't we mix some of these potent drugs together? Maybe this can help us create even more potent drugs. Yeah, so they had the drug library, as indicated here. And the drug library in our real problem, I think we had 30 drugs in there. And the problem was a binary problem. If a 1 would indicate include a particular drug in a drug mixture, and a 0 would indicate don't include it. Yeah? So it's a binary optimization problem that we had. But halfway through the optimization, the biologist said, you know what, whenever we have a particular drug, as indicated here by C and E, in a cocktail, then that has a very bad effect on the potency of that cocktail. So they decided to take out some of the drugs from the library and replace them with new drugs. Yeah? So that's essentially, they're changing the search space during the search. Yeah? So that's what we call a dynamic optimization problem. But this is a bit different from a standard dynamic optimization problem, because here the optimizer doesn't need to detect whether the problem is changing or not, because we're actually changing the problem deliberately, and we can tell the optimizer, I have taken out these particular drugs and I'm putting in these new drugs in, or I haven't put any new drugs in. Yeah, so they may just as well not put any new drugs in, just take drugs out. Yeah? So this is a bit different from a classical problem. And also in a classical problem, you would only have the objective function would only change over time. Yeah? In a classical decision, in a classical dynamic optimization problem, whereas here is the search space that is changing over time. And this is now my attempt to show you actually what this means. So imagine here you have a problem, a 5-dimensional problem. So we have a drug library of 5 drugs. Yeah. And let's say we are not changing any drugs. So then it means our initial search space here, X0, remains the same, yeah, throughout the search. So and then there's the other extreme. What happens if you're going to change the entire library? Yeah, you start off with that library that's making up X0, and then you're throwing that whole library away and changing it with new drugs. So you're changing completely your search space, and the only way probably to deal with this problem is to restart the optimization process. And then there's the interesting case in between, where you start off with X0 and you change only a small number of the drugs in your library, and that means some of the space in your search space remains the same. Some space is not anymore available, yeah, because you're replacing 2 drugs or taking them out, and then a new place emerges here. You know, and the challenge here is, how are you going to explore this new space as efficiently as possible, potentially using the information you've gathered here from X0. Yeah, so we have developed a method which we call permutation that is exactly doing this. You know, that method is trying to keep exploring that space that remains the same while intelligently trying to sample that space here. Yeah? And that's a method we developed 2010, if I look at the reference down here, and it worked at that time. And the interesting bit was, we didn't know that the biologists wanted to replace these drugs. They only told us this halfway through the optimization, and we needed to come up with a fix for that fairly quickly. So we came up with that method. It's not the best method. It's more than 10 years old. So if I would do the problem again, I would use slightly different methods. Back then we used an EA. It was a multi-objective problem, in fact, that we had here, and we used an IBEA, in case that tells you something. So it was a multi-objective evolutionary algorithm, and it worked. At the end, it helped us actually to discover drug combinations that were potent and had very low or no side effects. And we published that work in Nature Chemical Biology. And there is, of course, a lot that can be done here. For example, I mean, we haven't used Bayesian optimization back then. So if I were to do that again, the problem, I would use Bayesian optimization, and I would combine it with concepts from transfer learning, because there may be opportunity. If you're taking new drugs in, let's say in your drug library, and you know something about the properties, And maybe these properties are similar to some of the drugs you have replaced, and maybe you can use transfer learning to reuse the knowledge you've gained so far in the optimization process. And in our work, the biologists took out 2 drugs and put 2 drugs back in. Yeah, so you might also just take drugs out or take new drugs in rather than swapping, drugs. So we haven't looked at this as well. And there are also applications beyond drug discovery. For example, we used this technique, the permutation technique in clustering. So in 2018, we looked at adaptive encoding, and to deal with this adaptive encoding, we actually looked at permutation as one of the strategies. Yeah. Okay, another challenge. So now I'm moving on to a different challenge, which has nothing to do with the change of variables. So if you have any questions to the change of variables, maybe write them down so you can ask me later on. So objectives with different evaluation times. So that's now a problem we faced in multi-objective optimization. This is one of the classical pictures you can see to explain multiple objectives. Imagine you have a problem with 2 objectives, cost and comfort of a car, and you want to find a car that kind of is good in terms of both objectives. There is not a single solution here, but a trade-off of solutions here as indicated here. I wouldn't say probably the Lamborghini is very comfortable. If that would be a Bentley, that would be maybe more accurate picture, but I hope you get the point. Yeah, it's not a single optimal solution we have in a multi-objective problem, but a trade-off of solutions. Yeah, we call them also, that's also what we call the Pareto front. And here again, we had the drug discovery problem, and we noticed that actually some of the objectives were very fast to compute. For example, the cost of manufacturing a drug. Yeah, that's simply adding up the ingredients, potentially costs for electricity and so on, and the whole manufacturing process. And that all can be done with a simulation that is very fast to run. But also some of the objectives, for example, the potency and the side effects of drugs is something we cannot obtain by simulation. We actually had to mix the drugs ourselves and test them on an infected sample. Yeah, so these were slow objectives. So we had a problem where the complexity of objectives varies in terms of the durations of being evaluated. So we looked at this problem and thought, okay, I mean, we had to arrive at an optimal solution or discover this trade-off front as quickly as possible. How do we do this in this particular setting where the objectives vary in the time they take to be evaluated? So it was a problem no one looked at back then in 2013. So we defined the problem and published our work. And now actually it's great to see that quite a few research teams around the world are looking at this problem, which we have defined back then. And to give you an idea about this problem. So imagine again, a 2-objective problem, one fast objective and one slow objective. So imagine you have a standard optimization algorithm that is blind to the speed or to the duration it takes to evaluate an objective. That algorithm would evaluate a solution or a population of solutions for evaluation. And then whilst one of the objectives, the fast one, would be evaluated quickly, the other one would take longer. So that dashed line indicates the timeline. Yeah? So most of the time, if you look at that picture, you will not be using F1, yeah, the fast objective. So that fast objective will be just sitting there and unused. So that looks pretty much like a waste to do, yeah, because then the standard optimizer would wait until all objectives have been evaluated and then only generate the next batch of solutions. Yeah, so that is a naive algorithm. And then we looked at different strategies to deal with this problem. One could be is again a naive strategy, which we called fast first, and that strategy is doing as many single objective evaluations as possible, and then at the end it just evaluates the best solutions found on that fast objective, also on the slow objectives, in order to ensure that at least some of the solutions have been evaluated on all objectives. Yeah? And then there are the smarter strategies, what we call the interleaving. So the interleaving strategies may use evaluations on the fast objectives as a look ahead to decide which solutions to evaluate on the expensive slow objectives. Yeah? And this can be done in many ways. So we have looked at combining Bayesian optimization here also with transfer learning, and you can see here some of our publications. And the most recent one was in 2021, actually. Yeah. And Okay, and we noticed in our studies that the optimization performance was affected, for example, by the difference in terms of how slow is this, how much slower is the slow objective compared to the fast objective, by the correlation also between objectives. If you think about it, if you have a, let's say, a problem with two objectives and the objectives are positively correlated, then an approach like fast first is actually not so bad, yeah, because optimizing the fast objectives implies you're kind of also optimizing a bit the slow objective, yeah. Whereas if the correlation is very negative or non-existing, then the interleaving approach should be doing much better, yeah. And there are of course also scenarios where the standard optimization approach, the naive one that waits for all evaluations, that approach can do as well. The good thing about the naive approach is it's not introducing any bias into your search. Yeah? Whereas the fast first approach, you can think about it, the fast first approach will be really good in understanding where the good space for the fast objectives is, but will be doing really badly for the slow objectives. So future work, so one can think of various other methods to explore in future, yeah, in combination with Bayesian optimization. And one can also look at actually accounting correlations between objectives to drive search, something we haven't done yet. And so far, all the research on this problem actually looked only at two objectives. So no one looked at more than two objectives. So we have ongoing work that looks at more than two objectives. How can we generalize the methods we have here to more than two objectives? And then also what we have here we have objectives varying in the time they need to evaluate, but you could just as well also have constraints that vary in their evaluation times. And Julian, who has just finished his PhD with Kalyan, looked at something like that. Yeah. Looked at heterogeneous pair constraint evaluation times. Okay, here we have another resourcing issue that we faced, and that was what we call the ephemeral resource constraints. So if you think about, again, an experimental problem where you need resources to do evaluations, again, think about the classical example of drug discovery. To actually evaluate the potency of a drug cocktail, you actually need drugs to be available in order to mix them and then try them out. Yeah? And these drugs, or you also need the machine, a robot, to actually do the mixing in case you don't want to do it by hand. Yeah? And other resources, maybe if you run a very time-consuming simulation, you may need to have a supercomputer available. And these resources may not be available for all sorts of reasons in reality. Yeah? For example, the delivery of drugs may be delayed. So your algorithm tells you, I want to validate this particular solution, but it turns out if you go to your search, oh, I actually don't have a particular drug that the algorithm wants to use right now. Yeah, it can also be that you need skilled engineers to do a particular experiment, and these engineers may be out of office or on leave. So what do you do then? It may also be that the machine breaks down halfway through an experiment. Okay, so we looked at problems that how can you deal with these non-available resources. So we defined this problem here, and as before, this is our classical problem definition of a single objective problem, but we introduced here the notion of E, and also in this particular type of problems, we need to keep track of the time counter. Yeah? So our space E is the evaluable search space, and with ephemeral resource constraints, we need to make sure that if a solution is to be evaluable, then it has to be within ET, because ET represents the set of resources we have available at the moment, and therefore the set of experiments we can do right now. And this space ET may change over time, as I said before, because at different times during the optimization problems, you may have different drugs available at a particular time. You don't know upfront which machine breaks down or if a machine breaks down. So this space ET can either move around in a way you can predict or move around in a way you can't predict. For example, you don't know when the machine breaks down, but you would know when a particular engineer is on holiday. So you can plan, yeah? So that really depends on the resources you have to deal with. So this space ET, we defined this using a schema, what we call, and then we say only solutions that fall within the schema are evaluable. Yeah, so in that particular case, we have a 5-dimensional and a problem with 5 decision variables, and we say only solutions that have a 1 in the second decision variable and a 0 in the 5th decision variable can be evaluated. That asterisk indicates that we don't care whether that variable, these 3 variables are 0 or 1s. Again, this is a problem no one looked at back then, which was 2012. And only now, maybe 2 years ago, people have become interested in this. And right now I have actually a PhD project running with IBM that's looking exactly at this, at resource and constraints for drug synthesis. So here are some examples of these constraints. For example, you can have a periodic constraint that could refer to a skilled engineer being available only on 1 day of the week. So, and if you need that particular engineer to do a certain type of experiment, then on Monday you can't do these experiments because that engineer isn't available. And we found the best way to define this constraint is actually using if-else rules. Yeah. So we say if a particular condition is given, then the solution is available, otherwise not, or the other way around. It depends whether you model availability or non-availability. So we didn't come up from nowhere with these constraints, but these are actual constraints we had when we were dealing with our biologists. We had a periodic constraint, we had what we call a commitment relaxation constraint here, a particular machine. Once you set the parameters of the machine, you had to stick to these parameters for the whole day, because changing these parameters would involve cleaning the machine, and that would be done only at night. So you're essentially committing to a set of decision variable values for a temporary time. We had random constraints that model the breakdown of a machine at the random time step. We had more complicated constraints here, what we call the composite commitment composite constraints. Here the EA had to order resources preemptively, and once the resources arrived, the EA, or the optimizer, had to decide in which of the limited storage spaces we put that particular resource. And each resource had a limited reuse number, it had to be ordered in a batch, it had a shelf life, and so on. And these were real resources. In our particular problem, these were wafers that we used to measure blood samples. So, and if you're dealing with ERCs, we call them ERCs as an acronym, we need to decide who is in control of resource availability. For example, who is ordering these resources and who is making a decision about where to put these resources and which storage room. We also, so you may also need to combine scheduling with optimization, because you need to decide when to order these resources. And ultimately, you also want to find a solution that's good, but you also want to find that solution while wasting as little material as possible. So we have done a fair bit of work on this. It's a new problem. We came up with a taxonomy, and we came up with various methods to deal with these ERCs. Here are some very simple methods. I mean, the simplest one is probably just waiting until the resources become available or until that machine is fixed. Yeah, but as you can imagine, that's again, if you have to arrive at an optimal solution or near optimal one in a given time frame, waiting isn't the best approach. Maybe, yeah, you can do forcing. For example, if a particular drug you need isn't available, then maybe you use a different drug that is available. Yeah? You can do regenerate. You can maybe regenerate a solution until you have one that can be done given the available resources, and so. So these are simple strategies, and we looked at, okay, maybe we can come up with a more sophisticated strategy that tries to learn which of these simple strategies here should be used during an optimization problem, during an optimization process. So we used reinforcement learning to decide, to learn essentially a strategy that switches between these different basic strategies. And here our states were defined by the time counter, so how far into the optimization you are, and also by the quality of your population. So we used an EA here. And based on these two state variables, we decided which of these simple constraint handling strategies should be used. And that strategy performed better than using just one strategy throughout the optimization process. We also did a bit of theoretical analysis on these constraints. We did the Markov chain analysis to decide how to set the parameters of an EA. So that was in a very simple environment. And most recently, we got a paper accepted at this year's Gecko where we looked at graphs. How can we use graphs to define the resource dependencies. Yeah? So that was quite interesting work, and we combined this also with Bayesian optimization, and that's the first output we have from our relationship with IBM on this project. There is much more that can be done, as you can imagine, and the work we look with IBM is a drug synthesis, but there could be loads of other problems, as you can imagine, where this particular challenge or issue may arise. I think I have safety constraints here as well. I may look at them as well, because I think, okay, that's only 2 slides. So there is a problem we look at that has what we call safety constraints. So violating these constraints should be avoided at all costs, because something serious, irrevocable happens. For example, a robot breaks down and is destroyed, or potentially even you may put a life in danger. So at no cost you want to violate that constraint, because you don't want to kill someone, and you may have only one robot available. So as soon as the robot is broken, your optimization process is finished. And the middle here, we have an example in a movie recommender system. If you're recommending the wrong movies to a user, then maybe that person will actually leave, yeah? And you're losing out on money from that person for future renting. So yeah, so these are problems where you don't want to violate the constraints at all costs. And that's roughly how the problem looks like. You may not, so here we have a class, we have our, that line here indicates your objective function is a one-dimensional problem. And down here, we have the safety constraint is the dashed line. Think about it as a threshold that it's a maximization problem. Think about that dashed line as the threshold you don't want to go below, because if you go below, your optimization process is finished. And depending on the problem, you may know where this dashed line is, or you may not know where this dashed line is. Yep. So sometimes you actually have to learn where this dashed line is, but this only works if it's a problem where you can evaluate where you can violate the safety constraints a few times. Otherwise, it's very difficult to understand where is this line. So imagine you know where this line is. You can use the Bayesian optimization to predict or estimate whether a particular solution will be below this line or not. Yeah. So in this particular case, we say your objective function value cannot be worse than a given threshold. If it's worse than a given threshold, you're terminating your search just right here. So it's a problem we looked at 2011, and then it has become also very popular in the machine learning community. And we have now started to look at this problem again in a PhD project. And this problem can come again in various forms. For example, depending on the problem, you can evaluate the safety constraint a few times or more times. Yeah? The safety constraint, as I mentioned before, the threshold may be known or not. You may have multiple safety constraints in a problem. And you may start from a known set of safe solutions, yeah, or not. So it all depends on the problem you're actually faced with. Yeah? And also what information about safety constraint violation is returned to the optimizer varies as well. Depending on the problem, the optimizer may just know whether you have evaluated the safety constraint or not. In other problems, the optimizer may actually given the level of violation that happened. Yeah. So you actually have a gradient. Yeah. Okay, current state of play. Only very simple and the same type of safety optimization problems have been considered actually in the literature, and we've written a survey that we published in EKI that was 2020, and in that survey we reviewed 15 different algorithms to cope with safe optimization problems, and these were the only 15 algorithms that were out there in 2020. Yeah, but these algorithms, there were issues in terms of how people compared them, that there wasn't a rigorous way of benchmarking different algorithms. So what we have done is we came up with benchmark guidelines and also software for different algorithms. And we want to look at variations of safe optimization problems. So some of our work again got published at Gecko this year. And yes, you can come to Gecko and watch that presentation. Okay, summary. So I hope it has become clear today that there are loads of experimental issues that there may be in expensive optimization. I hope there are some issues in there that you haven't even thought about, because that's good, yeah. But after you've seen that presentation, I hope you think, oh, that actually is a real challenge. I mean, I haven't thought about this, but it makes complete sense to account for this in an optimization process. There is rather little software and guidelines on how to benchmark different algorithms for these problems. And I hope it has become also clear that a suitable way of dealing with these problems is actually a combination of scheduling, machine learning, reinforcement learning, and so on. Yeah, it's not classical optimization that we have to do here. And very important is also we need to validate these methods on real problems. Yeah? And no one so far looked at actually combining these challenges, multiple of these challenges in a single problem. We have only looked at one of these challenges at a time. So people can look at combining them as well. That is me. If you want to discuss any of these things further, any of the stuff I've presented today, you can also email me. Yeah? But now let's open up for questions.